AI is starting to split into two very different worlds. One where we can physically compute harder optimization problems in hardware, and another where we can quantify exactly how AI systems can be tricked by polished presentation. At the same time, the training side is getting more precise too. We're finally seeing why optimizers like Muon can beat Atom. Not just that they do. Keep watching, because the common thread here is control over computation, over evaluation, and over the geometry of learning. Let's explore the first paper, a 2048 spin bulk acoustic wave Ising machine for number partitioning and Sudoku. This paper from the University of Gothenburg, with collaborators at Oakland University and Tohoku University, introduces a bulk acoustic wave Ising machine, or BAWIM, that replaces optical time multiplexing with propagating RF pulse packets in quartz delay lines. The system uses two serially connected 20.5 MHz delay lines with 707 microcirculation time each, supporting 2,048 active spins out of 2,124 available pulse slots, and all-to-all couplings at 1.5-bit resolution. In max-cut tests on BikeMac graphs, the machine reaches 90% of the best heated ballistic simulated bifurcation result in 341 milliseconds, while a projected 16.455 GHz delay line could reduce this to 0.462 milliseconds. Across problem densities from 10% to 100%, it preserves up to 99.99% of the best simulated bifurcation score. The authors then extend the same hardware to number partitioning and Sudoku, showing that BAWIM outperforms the same simulated bifurcation baseline on both tasks and can solve a 9x9 Sudoku encoded with 729 spins, even when near ground state Ising energy does not imply a valid puzzle solution. The platform is also positioned as far more practical than coherent Ising machines, with room temperature operation, no post-selection, and about 4 orders of magnitude better thermal stability, while drawing 9.57 W in the current implementation. Let's explore the second paper. No hidden prompts needed. You can game AI peer review with presentation-only revisions. This paper, from the University of Texas at Austin, the University of Illinois Urbana-Champaign, the University of Texas at Dallas, and an independent researcher, shows that AI peer reviewers can be manipulated without hidden prompts, prompt injection, or any changes to methods, experiments, figures, equations, proofs, or numerical results. The authors introduce adversarial repackaging, a closed-loop attack that uses reviewer feedback to rewrite only presentation-level text, such as the abstract, introduction, related work, discussion, and conclusion, while keeping scientific evidence fixed. Across 3 mainstream reviewer models, Anthropic Claude Sonnet 4, Anthropic Claude Sonnet 4.5, and OpenAI GPT-5 Mini, the attack achieves a 75.1% attack success rate and a mean score gain of +1.21, with the strongest model-specific gain reaching +1.53 on Claude Sonnet 4. The paper further shows that narrative restructuring edits, like related work, repositioning, and analytical discussion expansion, outperform surface polishing, revealing a strength-weakness asymmetry in which reviewers are easier to impress than to convince, and often mistake the appearance of addressing a limitation for actually resolving it. The authors release a contamination-free rolling benchmark built from over 500 recent unpublished RxEve preprints paired with LaTeX and PDF sources, and argue that resistance to presentation-only gaming is a necessary condition for safe AI-assisted peer review. Let's explore the third paper, Why Muon Outperforms Atom, a Curvature Perspective. This paper, from National University of Singapore, Yale University, and the University of Minnesota, gives a curvature-based explanation for why Muon outperforms Atom in large language model pre-training. Using a 124M parameter nano GPT trained on FineWeb 10B, the authors show that at matched validation loss, Muon achieves a larger one-step loss decrease because it pays a much smaller second-order curvature penalty while matching Atom's first-order gain. They define this penalty through normalized directional sharpness and find that Muon and Atom have comparable update norms. So the advantage comes from a 1.76 times lower Atom to Muon NDS ratio, not smaller step size. On synthetic zip PCFG data with a 9M parameter nano GPT, increasing imbalance from S equals 0 to S equals 1 widens the NDS gap from 0.63 to 1.13, a 1.8 times increase, showing that heavy-tailed training data amplifies Muon's geometric advantage. A layer-wise decomposition further shows Muon's NDS shifts toward within-layer Hessian blocks over training, with the within-layer share rising from 14% to 44%, while Atom stays near 30%. The theory section proves that on structured quadratic models with low Kronecker rank Hessians and aligned gradients, spectral normalization spreads update energy across curvature modes, yielding smaller average NDS and, under strong curvature heterogeneity, a lower loss than gradient descent after the same number of steps. That's a wrap on today's AI paper highlights. Thanks for watching.